So what we're going to do today is we're going to pick up where we left off last time, and I'll try to talk about the alpha helix and clear up some mistakes that I made in the last discussion. But we're going to talk about secondary structure. We're going to talk about it in terms of alpha helix and beta pleated sheet. The alpha helical structure is what we introduced last time, and we emphasized that in the alpha helical structure, the protein is thrown into the spiral, and that within the spiral, there's hydrogen bonding that forms the alpha helix. The hydrogen bonding is such that there's hydrogen bonding between an amine of one amino acid and a carbonyl oxygen of another amino acid. And there's a pattern to that. It's said to be I plus 4. So that number 1 amino acid interacts with number 5, 5 with number 9, 2 with 6. Always the amino acid number plus 4. And that then throws the protein into this spiral. But there's another important type of secondary structure, and that's said to be the beta pleated sheet. And the beta pleated sheet now is going to be hydrogen bonding between adjacent strands or adjacent regions of the protein. And I'll draw this out and show you how this happens. And the beta pleated sheet, rather than being this nice smooth arc that we see with the alpha helix, the beta pleated sheet is a zigzag. And we'll talk a little bit about that. Now, the alpha helical region and the beta pleated sheet will interact one with the other, and also to some extent with the water, and they'll form the rudiments of the three-dimensional structure of the protein. But to get a proper three-dimensional structure of a protein requires the R group of each amino acid. In the alpha helix and the beta pleated sheet, we do not need to have R groups involved. Now we'll find out the alpha helix is formed predominantly from a subset of amino acids, but the R groups themselves are not involved in the generation of this structure. The three-dimensional structure of the protein comes about predominantly because of the way the R groups are interacting with the water around them. When you think about the R groups of the 20 different amino acids, I'm not going to ever ask you to memorize all those structures, but I'd like you to recognize that when we talk about R groups on the amino acids, that those R groups can be divided into 3 major groups. That is, the R groups can come as hydrophobic, where they're uncharged, methyls or hydrogens. They can come as though they're charged. These will be things like lysine and glutamate and aspartate. Or in the third one, they can come as being polar. These are going to be things like serine and threonine and tyrosine, where there are hydroxyls on them, and those will be polar. Now, when you hear polar and you hear charged, immediately home in on the idea hydrophilic. The charged and the polar molecules want to interact with water. When you think of the hydrophobic amino acids, think uncharged. And these are amino acid R groups that are not going to easily interact with the water. So when we begin to think about the three-dimensional shape of a protein, we're beginning to see the way the R groups in the protein interact with water and with one another. The R groups that are predominantly hydrophilic, that is, those are polar and charged, will turn around and face the water. Those R groups that are predominantly hydrophobic will then shy away from the water and fold up in such a way that they face one another. By having stretches of hydrophilic and hydrophobic amino acids, we now begin to see that the protein is generating its own three-dimensional structure. In theory, the lowest thermodynamic state of these R groups will determine the protein's three-dimensional shape. It's hard to overemphasize the importance of the three-dimensional shape of a protein in determining its function. Proteins carry out their jobs because of their three-dimensional shape. And because we have 20 different amino acids, and we can string them together in this myriad of different ways, we can now get an almost infinite variety of three-dimensional shapes out of these proteins. And those three-dimensional shapes will then determine their function by serving as an enzyme substrate or ligand receptor binding interaction. So we're going to generate a three-dimensional shape, an imaginary three-dimensional shape of a protein. And imagine how that three-dimensional shape within it is going to have something known as a binding pocket. And that binding pocket now may, because of its particular shape and also because of its charge, interact with a very specific kind of substrate if it's an enzyme. So an example, a common example, the one I'll give here, is that if we had an enzyme called sucrase, and the function of the sucrase is to convert sucrose into a molecule of glucose and a molecule of fructose, that sucrose molecule has a particular three-dimensional shape. That particular three-dimensional shape will fit precisely into the binding pocket of the three-dimensional, I'll say it again. The sucrose molecule will fit precisely with its three-dimensional shape into the three-dimensional shape of the binding pocket of the enzyme. Also within that binding pocket will be amino acids, and there'll be a certain charge distribution of those amino acids within the binding pocket. So there'll be a combination of the charge and the shape of the binding pocket that will provide the specificity of the enzyme for its substrate. That same idea, the same idea of a three-dimensional shape of a protein determining its function, is also true in the nervous system, where the three-dimensional shape of the protein may well be a receptor. And the molecule that binds to that receptor may be a neurotransmitter. And there needs to be a precise three-dimensional fit between the neurotransmitter and its receptor. That has a particular terminology. That terminology is called ligand-receptor interaction. This ligand-receptor interaction comes in a variety of different flavors. It may literally be an odorant that binds to a receptor in your nose that provides the sense of smell. It may be a hormone binding to a hormone receptor, and the hormone has to have its own three-dimensional shape, and the receptor has to have its own three-dimensional shape, and the two must fit lock and key. So the three-dimensional shape of a protein determines its function, whether it's an enzyme working on a substrate, or whether it's simply a molecule that's going to bind to a neurotransmitter or a hormone or an odorant in the world around us. We need that three-dimensional shape of these proteins. This whole idea, where we combine the secondary structure and the tertiary structure to form a three-dimensional shape, all of that is describing proteins that are free in the water. These are three-dimensional shapes of proteins that are out in the water column. But that begs the question. We said that an important characteristic of proteins is they form transmembrane proteins. They provide channels across phospholipid bilayers. So now how are we going to take these ideas of alpha helices and R groups and charge and put them across a phospholipid bilayer? And we'll talk about how we'll generate a channel by using the amino acid sequence, the alpha helical group, and then how the alpha helices go across the phospholipid bilayer and work in concert with other alpha helical groups to make a channel. Turns out, and I'll draw it on the board, but turns out you can't make a channel from a single alpha helix. It requires a minimum of 4 alpha helices to make a proper hydrophilic channel. And each of those alpha helices will, each alpha helix will spiral across the phospholipid bilayer independently and then interact one with another in such a way the hydrophilic side chains, R groups, will interact to make a channel. The hydrophobic will turn outward to the hydrophobic regions of the phospholipid bilayer, and we'll walk our way through that. But let's start where we were last time, and I'll see if I can straighten out some mistakes I made. So this is the alpha helix. And we said that the alpha helix was constructed from a sequence of amino acids. So each one of these red circles is intended to be an amino acid. And we said that amino acids in an alpha helix, hydrogen bond with one another. And that the hydrogen bonding occurs between the hydrogen in the amine occurs between the hydrogen in the amine and a carbonyl, oxygen, in another amino acid. But it's not just a random other amino acid. There is the rule, the so-called I+4 rule, which says that if we would start out here with amino acid number 1, it will hydrogen bond with amino acid number 5. So it's 1 plus 4 equals 5. So amino acid 1 interacts with 2, 3, 4, 5. Amino acid 2 interacts with 2, 3, 4, 5, and 6. And so forth. 3 will now go to 7. 4 will go to 9. And so we have this repeating pattern of the I+4. The other point that I made last time is I said that with each amino acid, we take a step of 0.15 nanometers. Where I got tangled last time, and some people pointed it out to me after the lecture, is that I said that each one of these amino acids turns by a particular number of degrees. I'm not even going to say it again. Each one of these amino acids turns by 100 degrees, so that it takes 3.6 amino acids to circle the alpha helix. So if you imagine this is a spiral staircase, then when you take a step, you only step up 0.15 nanometers. But when you take a step, unlike a typical spiral staircase, you turn more than 90 degrees. So you can imagine walking up a spiral staircase, you're facing this way, you turn, the next step will take you about this far. It takes you 100 degrees. That's a hell of a step. And so it only requires 3.6 amino acids to go around the circle once. But remember then that each of these amino acids is binding by hydrogen bonding to this I+4 arrangement. And that hydrogen bonding now throws this molecule into this spiral. And each amino acid moves by 0.15 nanometers, and it takes 3.6 to go the circuit. Now, I'll say this, then we'll come back to it. When you start thinking about these alpha helices going across the phospholipid bilayer, typically a phospholipid bilayer is about 60 to 70 nanometers. So that means it's going to take something in the neighborhood of 40 or more of these amino acids to wend their way across the phospholipid bilayer. And we'll talk about that a little later. So any questions up to here? So this is the alpha helical structure. And this is a classic form of secondary structure. And then, again, to emphasize the hydrogen bonding is from one amino acid to the next within the spiral staircase. That compares to something over here known as beta pleated sheet. The beta pleated sheet is more or less a zigzag. And I'll try to draw this way. Then someplace out here, there's a kink. Usually someplace around here, there will be a proline or a glycine that throws a kink into the amino acid sequence. It brings it around now, and now the points of the zigzag interact one with another. If this is the amino terminus, then this is the carboxy terminus. So this basically extends from the amino terminus, the molecule, around to the carboxy terminus. At this point, I'm going to put an R group. There are two R groups here interacting with one another. Then here we have an oxygen with a nitrogen and its hydrogen. This is now a hydrogen bond. Then again, we have on this one will be a hydrogen from an amine to an oxygen on the other one. But this is a hydrogen bond. Then we have the two R's. And then we have oxygen, hydrogen, hydrogen, oxygen, and the two R's, and so forth. Don't memorize that structure. That's not the important part. What's important here is that now we can throw this molecule into this secondary structure such that we have binding here at these zigzags. And the binding at the zigzags occurs within the protein. Because remember, this is the amino terminus of the molecule, and each one of these R groups, and each one of these hydroxyls, each one of carbonyl oxygens, each represents an amino acid. So this is the hydrogen bonding between amino acids in two strands of the same protein. Whereas this is occurring within the single strand. This is between two neighboring regions of the same strand. And this throws the molecule into this alternating zigzag pattern. Let me show it to you in a slide. So on the left-hand side is the alpha helix. And I won't go through this too much, but if you look at this, here is the nitrogen from an amine, here's its hydrogen, and it's now hydrogen bonded to this carbonyl oxygen. But if this is the, if this is the number one amino acid, it's going to hydrogen bond to 1 plus 4. This will be the fifth. If you walk your way through this and count it out, you'll see this one goes to the fifth. Now here's another hydrogen bond here. This is going to be the next amino acid because there's the amine, here's the carboxylic acid, here's the carbon with the R, there's the amine of the next one, and this now is going to hydrogen bond to the carbonyl oxygen 2 to 6. This pattern repeats itself over and over again, and the protein is thrown into the spiral. And each time we go from one amino acid to the next, we step 0.15 nanometers, and we go from, in this case, the amino end toward the carboxy end. What this is showing is what I just tried to draw on the board. This is showing something known as the anti-parallel beta-pleated sheet. In the anti-parallel beta-pleated sheet, we start up here at the amino terminus. Then we wend our way toward the carboxy terminus. Someplace out here in the blue, there'll be a kink. And the amino acid sequence turns around and now heads toward the carboxy terminus. This is said to be an anti-parallel arrangement. Now, that's what I've drawn on the board here. So now we have, here's the R group, oxygen, carbonyl oxygen, hydrogen, carbonyl oxygen, hydrogen, hydrogen bonding, R groups, OH, OH, R groups. So now we've drawn together through the hydrogen bonding regions of the protein. But rather than having it form into a spiral, it forms into the zigzag pattern. But to form the zigzag pattern, there has to be a kink out here someplace to head it round in the other direction. I'm going to go through the next one fairly quickly, and I'll try to draw it on the board and walk it through, but it's not as easily seen as this one. Yes, you had a question?
So for the beta-pleated sheets, I'm a little confused. So that's just one strand of amino acid that's just bent. At some point, it's not like two separate strands, but each other interacting.
So this is intended in this case to show two strands of the same protein interacting one with another. And you're absolutely right. Of the same protein. All right, let's walk it through again then. Right. Here's the amino terminus. We come through this amino acid sequence. We could have an amino acid sequence down here in the blue someplace. Within this blue, there's probably going to be a glycine or a proline. what glycines and prolines do is they're not very good at either beta-pleated sheet or alpha helix. So what it does is it forms a kink. It makes a sharp bend in the protein. So we have a bend in the protein here, and now, but if we were to walk one amino acid to the next, we continue to walk from the amino terminus toward the carboxy terminus. So we put a big kink in it, and now we're headed toward the carboxy terminus of the very same protein. But what you have to envision is down here, there's a turn, there's a kink. And I tried to show that on the board over here.
So it's all within the same protein.
It's all within the same protein. And then the other one is all within the same protein, but you notice this has the amino terminus at the same end. This is said to be parallel. Now, it's a detail. But what happens here is now these R groups and the hydrogen bonding are offset a little bit. So this makes the bond lengths a little longer. So the bond lengths of the hydrogen bonding are a little longer in this arrangement than they are here. And because of that, this interaction is not quite as strong. I'll try to draw this on the board and see if I can keep from confusing it completely. So to imagine this kind of arrangement, and this is said to be the parallel arrangement or the parallel organization. We'll start here with the NH2. That's the amino terminus. And then we'll just have a string of amino acids. Well, we can have those beta pleat sheet, actually. Then we have some alpha helix out here. Turns around, has some alpha helix up here. Now comes back down, and now forms this beta pleated sheet down to the carboxy terminus. This is the amino terminus of the molecule. This is the carboxy terminus. But you can imagine that within the molecule itself, this is also, this region in here, is toward the amino terminus. So these two stretches of amino acids are running in parallel, so we say this is a parallel organization of the beta pleated sheet. Now, I'm not going to emphasize the distinction between the parallel and the anti-parallel organization, so if you want to get your head around this, fine. But if you find this all too confusing, don't worry about it. But what I would like you to know is that we have these hydrogen bonds again between hydrogens on an amine and a double bonded oxygen. So we still, and this can occur out in the aqueous environment. So any questions to that? Yes?
Is one organization more common than the other? Like we see parallel or parallel more common?
I think the anti-parallel is more common, partly because the hydrogen bonding is a little, but I don't know. It just depends on how the molecule is folding up on itself. Anything else? Yes?
So do we examine like the alpha helix in itself? Like can it exist separately as from like an anti-parallel or parallel?
So the question is, can we have alpha helix appearing within a protein independent of either the parallel or anti-parallel beta pleat sheet? Yes, that's true. Now, I'm going to skate right by this, but if you get into the nuts and bolts of protein chemistry, you'll find that the alpha helix in an aqueous environment is not very stable and usually has to be surrounded by beta pleated sheet if it's going to be an aqueous environment to stabilize it, because the hydrogen bonding to the R groups on an alpha helix tends to make it fall apart. Oh, there's one more point I wanted to make. Dang it. This alpha helix, again, does not require the R groups. But having said that, there's a certain probability for these amino acids to make a alpha helix, and this is said to be malic. And this is derived from the single amino acid names for the amino acids. So this is methionine, alanine, leucine, glutamic acid, and lysine. These are hydrophobic. These are hydrophobic, and these two are charged. Now, that's a detail I'd never ask you about, but I do want to bring it up here to say that there are a subset of the amino acids that are more likely to form into an alpha helix. And if you're looking at an alpha helical stretch of amino acids, you're more likely to find those amino acids. But now, so any questions there? Now what I want to do is try to combine the alpha helical regions and the beta pleated sheet regions. So if we begin to look at the secondary structure of a protein, we could have this beta pleated sheet. Let's make this the amino terminus. You could have a kink out here, have some beta pleated sheet. Then perhaps we can go to some alpha helix and some beta pleated sheet. Another beta pleated sheet to say the carboxylic acid end. All I mean to say by this is that proteins contain regions of alpha helix and pleated sheet. And often, if you're reading a paper, you'll see structures like this. Where the protein structure is reasonably well known, and we'll see regions of alpha helix and regions of beta pleated sheet, and that's shown here. So these flat ribbon-like structures with the arrows on them are intended to describe pleated sheet structure. These regions of purple thrown into this sort of corkscrew, those are meant to be alpha helical regions. So you'll have regions within a protein that are alpha helix, others of which are beta pleated sheet, some of them running in parallel with one another, some running in anti-parallel arrangement with one another. And all of them, though, will also have these short segments which are neither alpha helix nor beta pleated sheet. So now we're beginning to see the protein forming a kind of configuration based on a combination of its alpha helical structure and its beta pleated sheet structure. All of this can be done without using any of the R group information. The next thing we need to do now, though, is to begin thinking about how we can superimpose R groups on this and finally fold this protein into a proper three-dimensional shape. So let's take the upper panel. And label this as the three-dimensional shape of proteins. Their tertiary structure is determined by the R groups. So again, it's the R groups and how they interact with water that largely determines the three-dimensional shape of a protein. So we'll label this as tertiary structure. The tertiary structure, which is just a fancy name for the 3D structure, derives from R group interaction with water. Well, I'll never ask you to memorize all of the 20 amino acids and their shapes, but I would like you to know that we can divide amino acids into 3 big categories. So we can say that amino acids can be charged. These are amino acids like aspartate and asparagine and lysine, and they can be polar. These are commonly ones that have a hydroxyl on them, like threonine and serine and tyrosine. Regardless, what I want you to recognize is whether we're talking about a charged or polar R group, that these R groups now are hydrophilic. And that there are other sets of amino acids which are nonpolar. And they are uncharged. These are amino acids like glycine and valine and leucine and isoleucine, where the side groups are single hydrogens or methyls or combinations of methyls. So there's almost no charge on these side groups. So when you think about these side groups, the R groups, being either nonpolar or uncharged, you now recognize that these are hydrophobic. So we're thinking, we're thinking here about amino acids having either a tendency to interact with water or not interacting with water, depending upon the characteristics of the R group. R groups that are charged or polar interact with water. Those that are uncharged tend to not interact with water. So let's now take a simplified view of this. Now I'm going to draw this as a kind of box. That's simply intended to describe the backbone of the protein. But that protein is made of amino acids, and each of those amino acids has an R group. Some of those R groups, and I'll show you these in blue, some of those R groups are hydrophilic. That is, they could be either charged or polar. Whereas others of the R groups these R groups are intended to be hydrophobic. Now remember, this protein is going to be surrounded by water. So you can imagine dunking this string of amino acids. You can even imagine it having some of its secondary structure. But now we're going to dunk it into the water. Now once it's underwater, the R groups now take a really predominant role in forming the three-dimensional shape of the protein. Because what we're going to see is that within that amino acid sequence, the hydrophilic amino acids will face the water. And the hydrophobic amino acids will turn away from water and interact with themselves. Such that when this protein folds up on itself, if this is the amino terminus and this is the carboxy terminus, some of these R groups are going to be facing outward. The blue ones are hydrophilic. They'll be facing the water. But there'll be stretches of these amino acids which are now interacting one with the other through hydrophobic bonding. So this string now, if you imagine this is a string, this string is now going to take on a certain three-dimensional shape. It's going to fold itself into its lowest order state. And by folding itself into its lowest order state, it's going to take its polar and charged R groups and predominantly turn them out to the water. And it's going to hide its hydrophobic R groups inward, one with the next. And this now, by allowing some of the R groups to face the water, other of the R groups being forced to face one another, this is now going to generate a three-dimensional shape of the protein. So the three-dimensional shape of the protein, the tertiary structure, results from hydrophilic R groups interacting with dipoles, let's say just water dipoles. But it also results from hydrophobic bonding between hydrophobic R groups. Hydrophobic bonding, some of you may have heard referred to as van der Waals forces. These are not very strong. Fundamentally, when you start thinking about hydrophobic bonding, it's kind of a default pathway. Everybody else who's hydrophilic or charged or polar turned out to the water. What's left are the hydrophobic guys who are now bonding with one another. So this is a low energy kind of bonding, but it still will end up, because of the hydrophobic nature of these R groups, they will turn inward and hide among themselves. Let's see if I can show this in a sort of simplified view. So this is intended to be a nicer image than what I put in the board, but it's telling a very similar story. So up here with the gumdrops, they're showing the hydrophobic R groups in green and the hydrophilic R groups in blue. And when this protein now folds up on itself, the lowest order state with respect to water is for the hydrophilic R groups shown in blue to interact with the dipoles on water, and for the hydrophobic R groups that are green to turn inward and interact with one another. This now generates the first level of three-dimensional shape of the protein. So you now begin to see how this protein reaches its lowest thermodynamic state simply by the interaction of the hydrophilic and hydrophobic R groups interacting with water or not. Now, for years, people have tried to take the amino acid sequence, knowing the charge on each of the amino acids, knowing how polar each of those amino acids was, or how hydrophobic, and tried to predict the three-dimensional shape of the protein simply by algorithms. And it hasn't worked very well. And probably one of the reasons it hasn't worked very well is that in biology, it's not just the lowest thermodynamic state which determines the shape of the protein. That in the process of making proteins, there are other molecules called chaperonins. And the chaperonins will now, using ATP, using energy, force these proteins into particular shapes. And the chaperonins will also check to make sure those shapes are proper. So we do have three-dimensional shapes, most of it dependent upon the hydrophilic and hydrophobic nature of the R groups. But that's not the end-all and be-all. This next image is one I'll show you just briefly. This is all of the amino acids. And again, if you're in a biochemistry course, you'd be asked to learn all of these structures. I'll never ask you to do that. But I like this figure because it divides the amino acids into charged, polar, and uncharged. So you can get a feeling here for a different kind of amino acid depending upon its R group and whether or not it readily interacts with the water. Now, the next piece I want to discuss here is something we're going to come back to over and over and over again. And it's really hard to overemphasize the importance of this next step. And what I'm going to do with this panel is simply say that protein function depends on its three-dimensional shape. So the function of a protein is derived from its three-dimensional shape. So the 3D, you can read tertiary. The 3D or tertiary structure determines a protein's function. Now, to try to illustrate that, what I want to think about is I'm going to take this squiggle and imagine that this is a protein that's been thrown into a three-dimensional shape. But there's a region within this that I want to emphasize, where this is the amino terminus and this is a carboxy terminus. Some regions will have hydrophilic R groups, and that will force them out into the water. Others will have hydrophobic R groups, so that through hydrophobic bonding, they'll be interacting one with the other. But what I want to emphasize here is a region I've pretty much arbitrarily drawn to represent the active site, more properly known as the binding pocket. If this particular protein, if this protein happened to be something like, say, sucrase. Sucrase is an enzyme that converts sucrose to a molecule of glucose and a molecule of fructose. But for this enzyme to do that, it requires a binding pocket into which the three-dimensional shape of, in this case, sucrose fits the 3D shape of the binding pocket. In addition to this 3D shape interaction, a kind of lock and key, there also has to be a certain amount of interaction of charge or polarity. There needs to be polar or charge interaction. Between substrate and enzyme. Now, the way these enzymes work is that when the substrate binds to this binding pocket, and you get this charge interaction between whatever charge there is on the substrate and the charge on the amino acids, that charge-charge interaction and the fit lowers the energy of activation to convert sucrose into fructose and glucose. You may have another enzyme that does the opposite, that it will bind will bind a molecule of fructose and a molecule of sucrose and bind a molecule of fructose and a molecule of glucose and form them into a molecule of sucrose. But again, everything has to fit just right into that three-dimensional shape of the protein, and then the charge interactions have to be right, so you lower the energy of activation of formation of that new molecule. We've told this story from the point of view of an enzyme and its substrate, but we could equally tell this story from the point of view of a ligand and a receptor. This term ligand is a derivative of the word ligate, to tie. And so we're going to tie the ligand to the receptor. And we're going to form something known as a ligand receptor complex. Now, this could take a number of forms. It can take the form of an antigen antibody complex. Or it could take the form of a hormone receptor. Or it could take the form of a neurotransmitter receptor complex. Regardless of how we think about it, whether it's an antibody interacting with an antigen, it's a hormone interacting with a receptor, or if it's a neurotransmitter interacting with a receptor, there has to be specificity based on the molecule shape. But in addition, there need to be charge-charge interactions so that hormone or neurotransmitter, whatever ligand it may happen to be, stays in that binding pocket for a certain amount of time because of the charge-charge interaction. In some cases, the neurotransmitter will open a channel. In some cases, the hormone will start a whole cascade of events. In some cases, the antigen binds to an antibody and starts another cascade of events, or in some cases, simply covers over the active sites in the antigen. But however we think about it, however we conceptualize it, what we're talking about is having a three-dimensional shape of the protein fitting precisely with the three-dimensional shape of whatever it's binding to. In the last few minutes, let me bring up the idea of the phospholipid bilayer. And I'll let you think about this between now and Wednesday. So what we're going to do is we're going to imagine here a phospholipid bilayer, just like we've talked about before. And we're going to generate a transmembrane protein. So transmembrane in a phospholipid bilayer. So this is the phospholipid bilayer. Now we have to think about how we're going to thread a protein across that phospholipid bilayer. We're going to make this the amino terminus. This protein is now going to go across the phospholipid bilayer and out into the extracellular space, so that this is now the carboxy terminus. This alpha helix is the same as the alpha helix we started out with. It's going to have a sequence of amino acids. It's going to have the hydrogen bonding. Each of these amino acids is going to step one to the next of 0.15 nanometers. The thickness of a phospholipid bilayer is usually 6 to 7 nanometers. So that means it's going to take 40 or more of these amino acids, one to the next, to form the spiral staircase to go across the phospholipid bilayer. What I'm going to leave you with here is what kinds of R groups would you expect on these amino acids that go across the phospholipid bilayer one time? And then think how we can manage to use a combination of alpha helices to generate an ion channel or a hydrophilic pathway, and we'll start on that on Wednesday.